Okay, hello everyone. Welcome. We are going to be working through the Unit 6 operations and exponents review. So a couple of things we need to be careful of. There will be function operations with graphs and inverse function graphs on the test. So please make sure that you are also studying those. Those are not on this review, but they are fair game on your test. So you may need to look back at your notes in order to see those. But we're going to go ahead and we're going to start with graphing. So we're graphing e to the x minus 3 plus 2. So our parent function here is f of x equals e to the x. That's our parent function. So the transformations in that exponent, because it's x minus 3, we're shifting to the right 3. And we are shifting, because of that plus 2 on the outside, we're shifting up 2. So right 3 up 2. Okay, our domain for any exponential is always negative infinity to infinity. And our range it starts at 0 to infinity, but it will reflect and shift depending on how our graph is being reflected and shifted. So it starts at 0 to infinity, but because we're going up 2, our range will actually be 2 to infinity, because our range will also shift up 2. Similarly with our horizontal asymptote, that horizontal asymptote starts at y equals 0, but because our graph is being shifted up 2, that horizontal asymptote will also shift up 2 and will be y equals 2. In order to find our y-intercept, we'll plug in 0. So we'll do e to the 0th minus 3 plus 2. So that's going to be e to the negative 3rd plus 2. Which we're actually going to rewrite, because whenever we have a negative exponent, we're going to drop that into the denominator and make that exponent positive. So it should be 0, 1 over e to the 3rd plus, sorry, not 3, but rather 2, plus 2. Okay, and we can leave it like that because we're not going to have a calculator, so we'll just leave that alone. Okay, I actually need to grab a second color, I think, so that we can Okay, so I'm going to go ahead and I'm going to graph my parent function. So for all of these graphs, our parent function points are always 0, 1, 1, whatever the base is, and then 1, 1 over the base. I'm sorry, negative 1, 1 over the base. So in this specific case, it's going to be 0, 1, 1, e, and negative 1, 1 over e. And we'll actually kind of approximate those points to 0, 1. 1e is approximately 1, 2.7-ish. And then negative 1, 1 over e is about negative 1, 1/3. We only use that approximation when we're talking about those specific points. So I'm going to go ahead and plot those. So plot 0, 1, 1, 2.7, and negative 1, 1/3. So our parent function will look something like this. And then I'll take those points and I'll do all my transformations. So I'll move it right 3 and up 2. So I'll take negative 1, 1/3, and I'll move that right 1, 2, 3, and up 1, 2 to be right about there. Okay, I'll take 0, 1, and I'll move that right 3 and up 2 to be right about here. And I'll take 1, 2.7 and move that right 3 and up 2 to be right about there-ish. Okay, and then I also need to remember that that horizontal asymptote is at y equals 2. So I cannot be crossing over the line y equals 2 for this final graph. So my graph needs to look something like this. So it's approaching that asymptote, but not touching it. So that red is my final. And then we can state our end behavior as our graph approaches negative infinity. So as we go to the left, our graph is approaching that asymptote of 2. And as our x values approach a positive infinity, so as we go to the right, our graph approaches a positive infinity as well. So that would be the answer to question number 1. Moving on to question number 2. So again, we're going to start by listing out our transformations. So our parent function for this, which I'll draw just kind of down here, our parent function is g of x equals 1/2 to the x. So then we have to determine what transformations are happening to that. Well, the negative out front, that's telling us it's going to be a reflection over the x-axis. We don't have anything in the exponent or any other number out front. And then that -3 on the end means that we're shifting down 3. Okay, so just because we have this as a 1/2, that doesn't mean that's a vertical shrink, because that 1/2 is our base. If we had a 1/2 out front over here with this negative, then that would be a vertical shrink. But because it is our base, it's being raised to that power, we just leave it as our parent function. So again, as always, our domain is going to be -infinity to infinity. With these exponentials, we can plug in any x value there. Our range starts, again, at 0 to infinity. But our range has been reflected over the x-axis and shifted down 3. That means our range, which had started at 0 to infinity, will now start at -infinity. And it will go until -3, because our graph was reflected. That's why we're starting at -infinity, and shifted down 3. That's why we're ending at -3. Okay, that also means our horizontal asymptote was shifted down 3. So that'll be y equals -3. And then for that y-intercept, again, we're going to plug in 0. So we'd say -1/2 to the 0th minus 3. Anything to the 0th power is just 1. So this would be -1 minus 3, which is, oh, sorry, I got ahead of myself, which is -4. So it would be 0, -4. And then we can go ahead and start graphing. So again, parent function points are going to be 0, 1, 1, comma, whatever the base is, which in this case is 1/2, and then -1, and we're going to flip that fraction because it'd be like 1 over 1/2, which is just 2. Okay, so again, right, it's -1, 1 over the base, but 1 divided by 1/2 is just a regular old 2. And then I can plot this. So I'll plot that parent function, 0, 1, 1, 1/2, -1, 2. So this is what my parent function looks like. And then I need to transform it to get that new graph. So I'll take that first point, so that 1, 2, I'll reflect it to get 1, -2, and then I'll shift it down 3 to get -1, -5. I'll take 0, 1, I'll reflect it to get 0, -1, and I'll shift that down 3 to get 0, -4. And then I'll take that 1, 1/2, I'll reflect it, and I'll move it down 3 to get -3.5. Okay, I need to remember again my asymptote is at y equals -3 for that final graph, which is right about here, so I don't want to cross that when I draw this graph. So that means my graph would look something like this. Okay, and then we can state our end behavior. So as our graph goes to the left, as x approaches -infinity, our graph is going towards -infinity. And as our x values approach a positive infinity, or as we go to the right, our graph is approaching this asymptote of -3. And so that should be that problem. So moving on to number 3. Ooh. Okay, so looking at number 3, we have 2 to the x plus 1 minus 3. So that means our parent function for this one is going to be that base, which is 2 to the x. So that is our parent function right now, and we just need to determine how it's being transformed. So that plus 1 in the exponent, that means that we're moving to the left one, right? It's the opposite of what we think. And that -3 on the outside means we are moving down 3. So all this is doing is moving to the left one and down 3. That domain has not changed. It's going to be -infinity to infinity. That range, again, starts at 0 to infinity. But because we move this graph down 3, that range is going to also have to shift down 3. And again, we're using parentheses for these ranges because of that asymptote, because we actually can't approach, we can't touch the value of -3 for our range, because the horizontal asymptote is also going to shift down 3. So that's kind of why our range uses parentheses rather than brackets, because we don't want to touch that asymptote. So we can't include it in our range. And then to find our y-intercept, we'll plug in 0. So we'll do 2 to the 0 plus 1 minus 3. So that'll be 2 to the first, which is just 2 minus 3. And then we can do that pretty easily, and we'll get 0, -1. So now we'll plot our parent function. Again, that's going to be 0, 1, 1, comma the base, which in this case is 2, and -1, 1 over the base, which in this case is 2. So -1, 1/2. So we'll go ahead and plot that. 0, 1, 1, 2, -1, 1/2. And so our parent function, and I'll move my hand in a second, will look something like that. And then I just have to transform all of those points. So I have to shift them to the left one and down 3. So I'll move this left one, this 1/2. So I'll get -2, 1/2, and then I'll move that down 3. So I'll get -2, -2.5. I'll take 0, 1, and I'll move that to the left one and down 3. So I'll get -1, -2. And then I'll take that 1, 2, and I'll move that to the left one and down 3. And that will give me 0, -1, which is also my y-intercept. And that is something we should note. As we are graphing, we should be kind of checking to make sure what we did on this section is matching up with how our graph is looking, which in this case it is. Again, we need to go ahead and plot that asymptote, which is y equals -3, because we want to make sure we're not touching that. And then we can kind of connect those dots and draw our graph, which will look something like that. Finally, we can do end behavior. So as x approaches -infinity, our graph approaches that asymptote of -3. And as our graph increases, as we approach +infinity, our y is also increasing. So it's also going to approach +infinity there. Okay, last graph. Okay. So this one actually has the parent function of f of x equals 1/3 to the x. So that means this 2 out front, we finally actually have a vertical stretch happening. So we have a vertical stretch by 2. That's what that 2 out front means. So we have a vertical stretch by 2. That 1/3 again is our base, so we're not really going to worry about that too much until we get our parent function points. That x minus 1 in that numerator, that -1 means we're actually moving the opposite direction to the right one, because it's the opposite of what we think. And then finally on the outside we have this +2. That means we're moving up 2. So the one out front is the vertical stretch, the one in the back is shifting it up 2. Okay. Again, domain is going to be -infinity to infinity. Our range, again, starts at 0 to infinity. It's not being reflected, so we don't have to reflect the range, but our range is being shifted up 2. The vertical stretch isn't really going to affect the range at all. It's going to affect our graph, but the only things that change the range are if we reflect it or if we shift it up or down. So reflection just means we'll start at negative infinity, and shifting up or down will determine what value we start or end at. So because we're shifting up 2, that range will start at 2, and we'll go to infinity. And you can also double check those with your graph to make sure you're on the right track. So our horizontal asymptote will also shift up 2. And the only things that affect the horizontal asymptote are going to be shifting up and down. The reflections won't affect those. And then we'll find our y-intercept. So we'll do 2 times 1/3 to the 0 minus 1 plus 2. Okay. So we'll have 2 to the 1/3 to the negative first plus 2. Hopefully we know that when we raise something to the negative first, we can actually flip that fraction. So it'll actually be a positive 3, or a positive 3 over 1, which is the same thing as 3 to the first, which again is the same thing as 3, plus 2. 2 times 3 is 6 plus 2, so that means our y-intercept is going to be 0, 8. Yay. Now we can graph. So again, going back to that parent function, those points are going to be 0, 1, 1 comma b, which in this case is 1/3, and then negative 1 comma 1 over b, which like we talked about before would be 1 over 1/3, which just becomes 3. So we'll plot negative 1, 3, 0, 1, 1, 1/3. Okay, so this would be our parent function. Okay, so we'll start with that first point, that negative 1, 3. So that's going to be vertically stretched by 2. That would take us to negative 1, 6, which is actually already off our graph. And then we'd remove right 1, so 0, 6, and up 2, so 0, 8. So that's actually our y-intercept, but it's not going to appear on this graph, so I'm actually not going to plot it because it won't fit. That's okay. So we'll take 0, 1, we'll vertically stretch it by 2, so 0, 2, and then we'll shift that to the right 1 and up 2 to get 1, 4. And we will plot that point because it does fit. Then we'll take 0, 1/3. We'll vertically stretch that by 2 to get 0, 2, we'll take 1, 1/3. We'll vertically stretch that by 2 to get 1, 2/3. And then we'll move that to the right 1 and up 2. And that will give us 2, and then 2 2/3. Okay. We'll plot that horizontal asymptote at 2. And then we can kind of connect our dots here and get our graph. So our graph will look something like that. I know we lost a point in that transformation, but that's okay. We'll state our end behavior. So as our graph goes to the left, as x approaches negative infinity, our graph is going towards infinity, right? It's going up. I'm going to write it below just for the sake of this room. And as we go to the right, as x approaches positive infinity, our graph is approaching that asymptote of 2. So make sure that when you do the asymptote, it needs to be the asymptote for your final function, not for the parent function. Okay, and that'll get us through graphing. So now we can kind of move on to solving. So starting here, the easiest way to do these is to get them in their most basic form. Can I zoom in at all? Oh, I can. Great. Okay. So here we have 4 to the x plus 7 equals 8 to the x plus 3. So we need to get these to have the same base. So I can rewrite 4 as 2 squared to the x plus 7. And I can rewrite 8 as 2 to the 3rd. So we need to make sure we are studying those exponent properties. So now that I have the same bases, right, and I'm raising a power to a power, I'm going to multiply those. So I'll get 2 to the 2x plus 2 times 7, which is 14. I don't have a ton of room. Equals 2, and we'll do 3 times x, which gives me 3x, and 3 times 3, which will give me 9. So because my bases are the same and they're equal, that means my exponents have to be the same. So that means I can set 2x plus 14 equal to 3x plus 9. And then I'll solve this. So I'll subtract 2x from both sides. And then I'll also subtract 9 from both sides. Okay, so 14, so these will cancel, and then 14 minus 9 will give us 5. 3x minus 2x will give us x, and these will cancel, so my answer is just that x equals 5. Okay, I'm going to do the same thing with number 6. So again, I need to get these in the most basic form possible. So we need to think about 32 for a second, right? Because 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So that means we can rewrite 32 as 2 to the 5th times x minus 1, or to the x minus 1. And then we can rewrite 4 as 2 squared to the x plus 5. Okay, so I'm actually gonna jump to setting my exponents equal kind of in one step, because I know that I have my same bases here. So I know I'm going to do 5 times x, which is 5x, and 5 times 1, or negative 1, which is negative 5, and that'll be equal to this exponent over here of 2 times x, which is 2x, and 2 times 5, which is 10. Okay. So I will subtract 2x from both sides, and I'll add 5 to both sides. And so 5x minus 2x, that gives me 3x. These 5's will cancel. These 2x's will cancel. And then I'll get that that's equal to 15. We'll divide both sides by 3. And that will give me that x equals 5. Okay. Moving on to the next one. This one's a little tricky because of the fractions, and there's a couple of different ways to think about it, so just be careful. I have 5/6 to the 4x, and then I have 36 over 25 to the 9 minus x. There's about 3 different ways to solve this, maybe more, but this is how I'm going to solve it. So I'm going to keep this 5/6 to the 4x kind of alone. I'm going to leave it alone. And then I'm going to think about this fraction over here. So hopefully we notice that, okay, I can rewrite 36 as 6 squared, and I can rewrite 25 as 5 squared. Okay, so that's some good progress, but that doesn't help us a ton, right? Because I have 5/6 and 6/5. So I want to be able to flip that fraction on one of the two sides. And so the easiest way to do that is, instead of raising to a positive power, I'm going to go ahead and I'm going to raise that to a negative power. So I can turn this into 5/6. Both of those are being squared, right? But because I flipped that fraction, I have to actually raise it to a -2. And then that I'll raise even further to that original exponent of 9 minus x. Okay. Now I have the same bases, so I can worry about setting their exponents equal, which I'm going to do up top here just for the sake of room. So I'm going to set 4x equal to, that's this exponent over here, equal to -2 times 9, which is -18, plus -2 times -x, which is plus 2x. Okay. So I will subtract 2x from both sides. And so that will give me 2x equals -18. And then I'll divide both sides by 2 to get that x equals 9. Okay. Other things you could have done is you could have gotten here and instead flipped this fraction by raising it to the -4x. You could have factored out a negative out of that and used it to flip. Regardless of how you did it, you should have gotten the same answer. Okay, moving on to the next one. Number 8 also has a couple different methods. So you could use 4 as your base, or you could use 2. I'm going to use 2 as my base just because that's always going to work, whereas 4 isn't always going to work. So I can rewrite 16 as 2 to the 4th. I can rewrite that 4 as 2 squared. And I can rewrite 64 as 2 to the 6th. Okay, so we need to make sure we know those. Okay. So that means I'm going to do 2 to the 4th times 2 to the 2 times 2x, which is 4x. 2 times -1, which is -2. Okay, and then I'm going to do is equal to 2 to the 6 times 8, which is 48x, and 6 times 5, which is 30. Okay, because when we raise a power to a power, we multiply. But when we multiply, we're going to add our exponent. So I'm actually going to go ahead and just do that in a kind of separate equation. So I'm going to add 4 to 4x minus 2. So that will give me 4x plus 2. And that'll be equal to the exponent on the other side, which is 48x plus 30. Okay. So I'll subtract 4x from both sides. And if that happens, it'll cancel on this side, so that means I need to subtract 30 from both sides. So that's going to give me, I'm going to jump up here because I'm running out of room. Negative 28 equals 44x. Right? So I'm like coming up here on both sides. And then we'll go ahead and divide by 44. And we can actually reduce that fraction because both 28 and 44 are divisible by 4. So negative 28 divided by 4 is a -7. And 44 divided by 8 is 11. So our answer is -7/11. So not the prettiest thing in the world, but it does end up working. And if you used a base of 4 for this specific one, it would work for that as well. Okay, moving on to the next one. Okay, so here we have, I'm gonna actually fold it over just so we can see. Here we have 216 to the 3x minus 1. So I can rewrite 216 as 6 to the 3rd to the 3x minus 1. I need to keep in mind that when I have a 6 alone, like I do right here, that's technically speaking 6 to the 1st, and I do need to include that. And then I'm multiplying that by 36, which I can rewrite as 6 squared to the 5x plus 3. Okay, so on the left side, that'll become 6 to the 3 times 3x, which is 9x, and 3 times -1, which is -3. It's equal to 6 to the 1st times 6 to the 2 times 5x, which is 10x. I knew the lights were going to go off. 2 times 3, which is 6. Okay, so now on the left side, I'm going to take that exponent, that 9x minus 3. And I'm going to set that equal to my exponents on the right. And again, because I'm multiplying, I can add those exponents. So it's going to be 10x plus 7, because I can combine that 6 and that 1. So then to solve, I'll subtract 9x from both sides. And then I'll subtract 7 from both sides. So the 9x's will cancel. -3 plus a -7 is a -10. 10x minus 9x is x, and then the 7's will cancel, so I should get that x equals -10. Okay, moving on to the next one. Again, number 10 you can do as base 2, or you can do it with base 4. Either way, you'll get the same answer, but I'm going to do it base 2, because I just like to get to the lowest number possible. So I can rewrite 4 as 2 squared. For both of these. Okay. And I can rewrite 64 as 2 to the 6th. Okay. So 2 squared to the 3x is going to be 2 times 3x, which is 6x. 2 squared to the negative x is going to be 2 to the negative 2x. And then 2 to the 6 times x plus 3. So 6x, and then 6 times 3 is 18. Oh, nope, sorry. Whoops. 2 to the 6x minus 18, or plus 18. Sorry, that's right. Okay, now I can go ahead and kind of combine those exponents on the left side. So 6x plus negative 2x is going to give me 4x. And that'll be equal to the exponent with the like base on the right side, so 6x plus 18. Okay, so I'm going to go ahead and subtract 6x from both sides. I'm kind of running out of room again. You can't see that. Okay, and so that's going to give me, I'm going to kind of sneak into this next one. That's going to give me negative 2x equals 18. So then I can divide both sides by negative 2. And I should get that x equals negative 9. Ooh, that was a squeeze. Okay, so moving on to the next one. Hopefully we can realize that those are two separate problems. So I'll fold my paper maybe, and that might fix it. The next one's kind of nice because I already have my like bases ready to go. So because these are the same base and they're equal, I can set negative 3a equal to a. We do have to be careful because a lot of people just want to divide by a from here, and you cannot do that. So instead we're going to add 3a to both sides. I don't like the way this is crumpling. Okay, whatever. We'll add 3a to both sides, and we'll get that 0 equals 4a. And when we divide both sides by 4, we'll get that a equals 0, which is an answer that we are allowed to have. So we need to be careful with that. 0 is an answer. Okay, moving on to 12. If I have 1/5, I can actually rewrite that as 5 to the negative first. Okay, right, because when we have a fraction, that's something to a negative power. I can also rewrite 25. I'm going to write that as 5 squared, and I'm raising that to the 2x plus 3. And then 625 is actually 5 to the 4th, right? Because 5 times 5 is 25, times 5 is 125, times 5 is 625. And because it's in the denominator of this fraction, that's going to be 5 to the negative 4th. Okay, and then we can focus on these exponents. So we have 5 to the negative first times 5 to the 2 times 2x is going to be 4x. 2 times 3 is going to be 6. And then once I get there, I know that I'm going to have my like bases, so I can start dealing with my exponents. So again, because I'm multiplying, I'll be adding those exponents together, which will give me 4x plus 5, right? Because 6 minus 1 is 5. And that'll be equal to the exponent on the other side, which is negative 4. I'll subtract 5 from both sides to give me that 4x equals negative 9, and divide by 4 to get that x equals negative 9/4. Okay, next section. Okay, so we have two functions here, and we want to perform each operation. So we're doing addition, subtraction, multiplication, division, and then compositions. And we want to state the domain for everything except for the compositions. So we're starting with the first one, f plus g of x. So we'll take f of x and we'll add to it g of x. So we'll do x plus 3. Okay, x plus 3, which is f of x, plus g of x, which is 2x squared, plus 4x, minus 6. That's what this is equal to. So with that happening, we'll combine our like terms. So 2x squared can't be combined with anything. 4x plus x is going to be 5x. And then 3 plus that negative 6 is going to be minus 3. And so that would be our solution. However, this does also ask us to state the domain for everything. So I do want to talk about the domain of our original functions for this. I'm going to zoom out just a little bit. I do want to talk about the domain for those original functions. So we should hopefully know that f of x equals x plus 3. That means that f of x has the domain of negative infinity to infinity. Right, because that's a linear function. So I can plug any x value into that. It does not matter. I won't have any negatives under the radical, any zeros in the denominator, none of that. So I'm good there. And then g of x, again, I can plug in any x values into that. There's no radicals, denominators, nothing like that. So that means g of x also has the domain of negative infinity to infinity. So if both of these have that domain, that means that f plus g of x will have that same domain. And additionally, we can look at this function and understand, again, no radicals, no denominators, nothing like that, so my domain is solid. So next we'll do f minus g of x, so we'll take f of x, and we'll be subtracting the entirety of g of x. So we need to make sure when we do this, we are distributing that negative out to that entire function. A lot of people just want to put it to that 2x squared, but it needs to go to everything. So really this should be x plus 3 minus 2x squared minus 4x plus 6. So I'm distributing that negative out to everything. So again, negative 2x squared can't be combined with anything. Negative 4x plus x is going to give us 3x. I'm sorry, negative 3x. And then 3 plus 6 is 9. X. That's ugly to look at. Okay. And again, our original domains were the same. We can look at this function, see no radicals, no denominators, so we'll also say our domain is negative infinity to infinity. We can plug anything into that. Next, we'll be multiplying these two together. That's what this f times g of x means. And I'm actually going to use the box to do so. So I'll be multiplying f, which is x plus 3, times g of x, which is 2x squared plus 4x minus 6. So I'll do 2x times x, 2x squared times x, which is 2x to the third. 2x squared times 3, which is 6x squared. 4x times x, which is 4x squared. 4x times 3, which is 12x. Negative 6 times x, which is negative 6x, and negative 6 times 3, which is a negative 18. Okay, so that means that this will be equal to, and we'll combine our like terms as we go. 2x to the third, that can't be combined with anything. I can combine this 6x squared with this 4x squared to get 10x squared. I can combine this 12x with this negative 6x to get plus just a regular old 6x. And then I can't combine that negative 18 with anything. And again, the domain will stay the same, negative infinity to infinity, because I can plug in anything to that and nothing funky will happen with the outcome. Okay. So the next thing we're doing is f divided by g of x. I'm going to pull this paper down just a little more. So with f divided by g of x, we'll take that f of x equation, which is x plus 3, and we'll divide it by that g of x equation, which is 2x squared plus 4x minus 6. Now, normally we would think to stop here. The problem with this is that we can actually factor this denominator. So we're going to go ahead and factor that. So hopefully we notice that we can take out a 2. There's a GCF of 2 there. So we'll get 2 on the outside, x squared plus 2x minus 3. Because 2x squared, 4x, and negative 6 are all divisible by 2. So I took that out front. Then we'll actually use the box to factor the rest from there. So we'll take this, I don't know if I want to put the box there. It's a little tight, it's okay. We'll go over here. So we'll take the box, we'll put x squared up top. We have negative 3 down here, so we want something that multiplies to a negative 3x squared, but adds to 2x. So our two numbers there are going to be 3x and negative 1x. So we can take out an x from this first column, a 3 from this second column, an x from this first row, and a negative 1 from this second row. So that means that this would be x plus 3 over 2 times x plus 3, x minus 1. And funny enough, look at that, something is gonna cancel. Those x plus 3s are gonna cancel there. So our actual new function is gonna be 1 over 2 times x minus 1. Okay, so this will be our new function. And we also do need to worry about the domain here, because the problem with the domain here is that not only can x not equal 1 because of this x minus 1 in the denominator, but it also can't equal negative 3, and that's due to the fact that by canceling these out, we technically speaking created a hole in our graph. So by taking x plus 3 over x plus 3, that creates a hole. So really our domain should be, and I'm going to kind of draw it over here, negative infinity to negative 3, because there's a hole at negative 3 due to these two factors canceling, union negative 3 to 1, because our denominator can't be 0, so that x minus 1 can't be equal to 0, so therefore x can't be 1, union 1 to infinity. So this is the domain we really, really have to worry about, because at no point in time from the beginning to the end of this problem, this division problem, can our denominator be 0. So right here, when we factored it, if x was equal to negative 3 at this point, our denominator would be 0. So we got to make sure we're excluding that. Okay, next we're doing a composition, f of g of x. So that means we're going to be taking g of x and plugging it into that f equation. So we'll be doing f of g of x, which is 2x squared plus 4x minus 6. So that means everywhere we see an x in that f equation, we'll be plugging in g of x. So we can also write this as this. Those mean the same thing. So like the little f of g of x, all that is the same. So that'll be 2x squared plus 4x minus 6 plus 3, right? Because f of x was x plus 3. So we plugged in this whole thing for x, and then we added that plus 3. So our equation will be 2x squared plus 4x, and then negative 6 plus 3 is negative 3. And we don't need to state the domain and range for the composition, so we'll just leave it like that, and that would be our answer. Next, we'll do g of f of x. Okay, so that means everywhere we see an x in that g equation, we're plugging in x plus 3. Again, we can also write this as g of f of x. Okay, so we'd plug this in. We have 2 x squared, so we'll plug in x plus 3 squared, plus 4x, so we'll plug in x plus 3 there, minus 6. Okay. The biggest issue with this one is that x plus 3 squared means we're going to have to do the box in order to multiply that out properly. So I'm actually going to maybe fold this over, maybe? Yeah, okay. So I'm going to multiply that x plus 3 in the box to help me out a little bit. So I'll do x plus 3 times x plus 3. So x times x will give me x squared. X times 3 will give me 3x. X times 3 will give me 3x. And then 3 times 3 will give me 9. So that means I can replace this x plus 3 squared with x squared from here. 3x plus 3x, so that's going to be plus 6x. And then also plus 9. And I'll keep everything else the same. So now I can distribute those coefficients. So 2 times x squared is going to be 2x squared. 2 times 6x is 12x. 2 times 9 is 18. 4 times x is 4x. 4 times 3 is 12. And we'll keep that negative 6. So to get our final equation, we'll just combine those like terms. So 2x squared isn't going to combine with anything. So this will just be 2x squared. 12x can be combined with 4x to give us plus 16x. And then 18 plus 12, that's going to be 30, minus 6 is going to give us plus 24. And so this would be that final function. Okay, moving on to the next section. So the next section says determine whether the function has an inverse. If it does, we want to find the inverse and state any restrictions on the domain. Okay. So looking at this original function, we see that it's 4x minus 7. That means it's linear. So that means, yes, it's going to have an inverse because it passes that horizontal line test. Okay, because anywhere I draw a horizontal line, it's only going to touch once. So yes, it has an inverse. So I'm going to state my original domain and range. So for my original, my domain, I can plug anything into that function, right? Because it's linear. I can plug in any x value, and I'll get out any y value. Right? And again, we know that because it's linear, and because there's no denominators, no radicals, nothing like that. So now in order to solve it, we're going to flip x and y. So we'll change this to x equals 4y minus 7. And we want to solve for y in order to find our inverse. So that means we're going to add 7 to both sides. So we'll get x plus 7 equals 4y. And then to solve for y, we'll divide both sides by 4. We got to divide the entire thing by 4. So that will give us x plus 7 over 4 equals y. Once we solve for y, we do need to write this in proper notation. So we put f inverse. So we put that -1 first. A lot of people were putting that after the x. It needs to go in front of it. F inverse of x equals x plus 7 over 4. And then we don't have any restrictions on the domain, partially because, again, we don't have any x's in the denominator. We don't have any radicals. But the other reason is for this inverse, our domain is going to be the same as the original range. So the original range was -infinity to infinity. So our new domain is also going to be -infinity to infinity. And so this is how we would notate it. So just make sure you're being careful with that. For our second function, we have x squared minus 16. So this is a parabola or a quadratic, and so it has a rough U shape. It's opening up. And it has zeros actually at -4 and +4. But just because of the fact that it's a parabola, it fails that horizontal line test because it intersects twice. And it does ask us to explain. So we would say no, because it fails the horizontal line test. So this does not have an inverse because it fails the horizontal line test. You don't need to write like an entire paragraph for me, just fails the horizontal line test is enough. Okay, and moving on to number 16, which is probably the trickiest out of these. I guess I have enough room. So this is actually a rational function. So hopefully we remember that rational functions look something like, this is not a great graph, but it looks something like this. And this is actually going to pass that horizontal line test because of the asymptotes. So yes, this is going to have an inverse. So we need to go ahead and try to find that. So again, before we get started, I'm going to state the original domain and range. So the original domain of this function, right, that denominator can't equal 0. So the original domain is that x cannot equal, if I set that equal to 0 and solved, so x cannot equal 2/3. Okay, again, that's coming from the fact that I set the denominator equal to 0 and solved. And the original range is determined by that horizontal asymptote. So if we flash back to our rational functions, we should remember that because our degrees are the same, our horizontal asymptote is when we divide those leading coefficients. So our range is everything except for that horizontal asymptote of 5/3. Okay, and we'll just keep that in mind as we move forward. You can write it in interval notation. I actually would prefer that you do, but for the sake of room, I'm not going to do that here. So just keeping that in mind. So when we want to solve this, we're going to go ahead and we'll flip x and y. So we'll say x equals 5y plus 1 over 3y minus 2. Okay, so the problem is we have some fractions happening and we want to get y's all together outside of the denominators on their own on one side. So we're going to multiply both sides by that denominator to kind of clear it out a little bit. So x times 3y is 3xy, or 3yx, it's the same thing. And x times negative 2 is minus 2x. On the other side, that denominator and what we multiplied by will cancel, leaving us with 5x plus 1. Okay, so I'm going to move the y's to one side, so I'll subtract 5y. So we'll get 3xy minus 5y minus 2x equals 1. But I want to get those y's alone by themselves, so I'm also going to add that 2x back. Okay, so that should give me 3xy minus 5y equals 2x plus 1. So now hopefully we see that the y's are kind of collected on the same side, and so because of that I can actually factor out a y from both of those. So 3xy divided by y would leave us with 3x, and this negative 5y divided by y would leave us with minus 5. So now just to get y alone, we'll divide both sides by what it's being multiplied by, which is 3x minus 5. And so we'll get that y equals 2x plus 1 over 3x minus 5. And then all we have to do is change that y and rewrite it as f inverse of x. And we need to state our domain restriction. So again, our original range was that y cannot equal 5/3, so that means in our domain, x can't equal 5/3, and we should also be able to check ourselves by if we set this denominator equal to 0, because our denominator can't be 0, we would also get 5/3. So the domain for this is negative infinity to 5/3, union 5/3 to infinity. So everything except for that 5/3 there. And that would be our solution. Okay, we're on the last problem. Okay, so the last thing that we need to do is verify using compositions that f of x and g of x are inverses of one another. So we're not trying to solve for the inverse. We're going to use composition. So we're going to do f of g of x, and we're also going to do g of f of x. This is how we check compositions. We do f of g of x and g of f of x, and both of them should output x. So we're going to take g of x and we'll plug it into this f equation. So f is 4 times x, so we'll replace that. So x minus 9 over 4 plus 9. Once we do that, the only operations we can do are those that are already listed on our page. So 4 times x minus 9 over 4, this 4 and this 4 will cancel, leaving us with x minus 9 plus 9. And x minus 9 plus 9 is just x. That's what we want to get out. And then we'll check the other direction. So we'll take g of x, which is x, so replace that. So 4x plus 9 minus 9 all over 4. So again, I plugged in 4x plus 9 for x. And again, whatever's already listed here, that's all I can do. So in that numerator, 4x plus 9 minus 9 will leave us with just 4x. and 4x divided by 4 is just x. And so it works, and that's how we verify. And that should complete our review. Okay.